This lesson deals with an Astable multivibrator. You can find these notes in the ECE402 ebook in Chapter 7, starting on page 8. In our last video, we looked at the monostable mode of the 555 timer. And what that meant was that there was one stable state. We hit it with a pulse of varying length, and then it created a pulse of a fixed length out. But after some time, it went back to 0 volts again. So there was one stable state, 0 volts. The astable mode of the 555 timer is a little different. What we're going to show shortly is that it has no stable state. It just simply goes between two states. In other words, like a square wave. What I want to show is that the voltage across the threshold will charge up, then discharge, charge up, and then discharge. Now in this configuration, we have two R's and a C. And here the threshold and the trigger are tied together. And the discharge transistor is tied here between the two. Let's even figure out how this thing works. At t equals 0 plus, when we first turn it on, let's assume the capacitor is uncharged. So the voltage across here is 0. And that's going to be the trigger voltage and the threshold voltage. Let's go back to page 1 where we have our functional block diagram and figure out what happens. If the trigger is at 0 volts, here I have 1/3 VCC and 0, so that difference is positive. That's going to give me a logical 1 on the set line. And then I have a threshold that's 0 volts, but this is 2/3 VCC, so that difference is going to be negative, so I'm going to go low. I'll get a logical 0 here. So I have a 1 on the set line, a 0 on the reset line, so the output is set high, and its complement is set low. Now when this is set low, this transistor is cut off. The RS pin is actually tied back to the power supply, so this is cut off the whole time. So our output goes high. And with the discharge transistor cut off, I now have an RC charging circuit, but now I have two series resistors. So it's going to be the same equation we had last time, except that we now have an R1 plus R2. My threshold voltage, which is also my trigger voltage, which is also my capacitor voltage, is going to be some VCC, power supply, times the quantity 1 minus e to the minus t over R1 plus R2 times C1. So this will be valid for t greater than 0, and we'll take a look at what's going to happen next. Okay, now when the capacitor begins to charge, it's eventually going to cross 1/3 VCC. So let's see what happens when that occurs. Go back to our functional block diagram. So now we have the trigger coming up now to being greater than, just slightly greater than 1/3 VCC. So that difference now is negative. So it's going to go to logical 0. And this is still less than 2/3 VCC, so the difference is negative, so we go to logical 0. So this is the case where we have no change in the output. Our output was high, and it stays high. Let's go back to that graph and just see what it looks like. So here I got my charging, and coming up past 1/3 VCC, and then the next point to take a look at is 2/3 VCC. Let's recap where we are. So we started out at t equals 0. The output went high. The discharge transistor was cut off, and we now have an RC charging circuit. We saw that as we crossed 1/3 VCC, nothing happened to the output. And now we're going to get to 2/3 VCC. So we'll take a look at our functional block diagram and see what happens. The trigger is at 2/3 VCC, but 1/3 VCC minus 2/3 VCC is negative, so that's still logical 0. But now this crosses 2/3 VCC such that this difference is positive, so we go to a logical 1. That means that the output goes low, complement goes high, and we now saturate the discharge transistor. So what's going to happen here, then we're going to short this point back to ground. So I'm going to have R1 in parallel with C1, and then the battery through R2 back to ground. What's going to happen? Well, when you put an R and C in parallel, they're going to start to discharge the initial condition, and so we get to this 2/3 VCC, and then at T2, say plus plus, we start to discharge. Now what's going to happen to our functional block diagram? Well, this is still greater than 1/3 VCC, so this is still logical 0, but now this drops below 2/3 VCC, but just a little bit. And that now makes this difference negative, so we go to logical 0. But that means there's no change in the output. So the output went low, it stays low, and now we have this R and C in parallel. Let's see if we can figure out what's going to happen. Well, the capacitor has an initial condition of 2/3 VCC, and we just simply have an RC decay. You could do the A and B if you want to, but just kind of think about what's happening here. Have an initial condition. We're just basically going to discharge that charge on the capacitor, and we'll go to 0 volts. So we're starting out at time t2, so it's going to be e to the minus t2 as a quantity, over now R1 C1, and that'll begin to discharge towards 0. Let's again recap where we are. So we started out with an initial condition of 2/3 VCC, and we started to RC decay. Now suppose that we drop a little bit below 1/3 VCC at some time T3 plus. Okay, let's see what happens with our functional block diagram. The threshold is still less than 2/3 VCC, so this minus 2/3 VCC would be negative, so it's a logical 0. But now the trigger is less than 1/3 VCC, so the difference of these two is slightly positive, and that makes the output go high, which is a logical 1, which makes the output go to 1, and the complement go back to 0. It's going to cut off the transistor. So let's see what happens in our circuit. So if we go back here now and we cut off the transistor, we had an RC decay, dropping us below 1/3 VCC just a little bit. But now we're going to go back and try to charge towards VCC again. So what's going to happen? Well, initially we're going to start to go above 1/3 VCC. So let's go back and look at that functional block diagram again. And now this voltage is slightly greater than 1/3 VCC, so that makes the difference negative, which makes this logical 0. This is still less than 2/3 VCC. That still stays 0, so there's no change in the output. So the output went high, and it stays high as we pass through T3 plus and plus plus. Let's even solve for the equation now for the charging capacitor. It's going to be similar to this one, but we're having an initial condition, so it'll be a shorter amount of time. So our threshold voltage, which is our trigger voltage, which is our capacitor voltage, is some A plus B times e to the quantity T minus T3 over now R1 plus R2 times C1. And the value of this at T3 minus is the same as T3 plus, which is 1/3 VCC. Plugging in T equals T3 becomes e to the 0, so we just have A plus B. Now if we let T approach infinity, this circuit above is going to charge to VCC. Never will make it there, but it doesn't know that. That's going to be taking this equation as T approaches infinity, which would be e to the minus infinity, which is 0, so it's equal to A. We can put the equation together for our charging capacitor starting at time T3. So A is equal to VCC, A plus B is equal to 1/3 VCC, so that makes B equal to minus 2/3 VCC. So that's our expression now for the capacitor voltage, or the threshold, or the trigger voltage. Let's see what happens next. At time T3, the output went high, the discharge transistor was cut off, and then we started to charge towards VCC. At some time, say T4, we're going to cross 2/3 VCC again. So let's see what happens with our functional block diagram. So our trigger is greater than 1/3 VCC, so that difference is negative. So this is still logical 0, but now the threshold crosses 2/3 VCC, so this difference is positive, and that gives me a 1 on the reset line. Output goes low, complement goes high. I'm going to saturate the transistor. So the output's going to go low, and then when we saturate the transistor, we now put R1 in parallel with C1, so we begin to start to discharge. So at time T4 plus plus, we've dropped below 2/3 VCC again. So let's see what happens. So again, back here, now we have the threshold dropping below 2/3 VCC, so the difference between this and this is negative, so we go back to logical 0, and there's no change in the output. So we went low and we stay low, and now we begin to discharge. But this is exactly the same as what we were doing over here. So the process is going to repeat itself. Let's next predict the time intervals, T2, T3 minus T2, and then T4 minus T3. Back on page 8, we had a formula for the charging of the capacitor going from 0 to T2, and that was equal to this expression right here. I'm going to replace T by T2, and at the value of T2, we're equal to 2/3 VCC. So we can now solve for the interval T2 minus 0, or just T2. Well, this is going to cancel with this, not dependent on that. Bring this over to here. You get 1 minus 2/3, which is 1/3. This on the other side of the equation. Take the reciprocals of both sides, and that 1/3 becomes 3. Natural log of this, cross multiply by R1 plus R2, C1 times the natural log of 3. Left off the steps here, but I think you could just fill those in if you needed to. So it's the same formula we had for the monostable, except that we've got two series resistors. Now what about the interval between T3 and T2? Well, we had this expression on page 9. For the charging capacitor, it was 2/3 VCC e to the minus T minus T2 over R1C1. And now let's evaluate this when T is equal to T3. Let's go back up here for a second. So when T is equal to T3, we're at 1/3 VCC. So 1/3 VCC is that equation evaluated when T equals T3. Again, the VCC's cancel. Here the 3's cancel. If I leave the 2 here and put this on the other side of the equation, I get an e to the plus. Take the natural log of both sides. So I get the natural log of 2 and cross multiplying by R1C1. So the interval of T3 minus T2 is equal to the natural log of 2, which is about 0.693 times R1C1. I'm going to call that time T sub L. That's the time that we're low when we reach steady state. This first interval is a one-shot. It just happens once. It's really our transient response, and then we eventually begin to repeat the intervals of high and low. Let's calculate the next interval, T4 minus T3. To be able to solve for the interval T4 minus T3, we need the equation we had back on page 10, which is shown over here. For the capacitor voltage, or the threshold voltage, it was VCC minus 2/3 VCC e to the minus quantity T minus T3 over R1 plus R2C1. So the value at T equals T4 is 2/3 VCC, so plug that in for T4. Didn't show all the algebra here, but I'll let you figure it out. The difference between T4 and T3 is R1 plus R2C1 times the natural log of 2, which again is 0.693. And this is going to be the interval where the output's high, so I'm going to call that T sub H. So we're getting a repeating, it looks like a square wave, depending on the time intervals that we have here. We'll talk about that in just a second. So the period of this would be the summation of the last two results. So we have this term here added to 0.693 R1C1. So adding those two together, I then get a common 0.693, a common C1, and then I have R1 twice, so 2R1 plus R2. Take the reciprocal of that, we get the frequency, and 1 over 0.693 is 1.443. Another thing we'll find handy is a thing called a duty cycle. This is the time that it's high to the period, and that would be our T4 minus T3 over T4 minus T2. That difference was natural log of 2 times C1 and then R1 plus R2, and the same expression here, and the natural logs of 2 cancel and the C1s cancel, and I get R1 plus R2 over 2R1 plus R2, and then times 100% is usually how it's stated. Now, if the resistor R1 is much, much greater than R2, if you look at the algebra here, then this term drops out and you just get basically a half. So you get a duty cycle of 50%. That would mean a square wave, basically. The other case is if R1 were much, much less than R2. In other words, this is much, much smaller than this, then our duty cycle approaches 100%. What does that mean? Well, basically you're going to have an interval that goes low that's very, very narrow, and then for the rest of the cycle, from here to here, will be high. We'll find that useful. We can use that for a trigger on a monostable. And this is the astable mode of a 555 timer.